First of all, welcome to the course. By now you should be well into Unit 1 and ready to take a closer look at the process of using mathematics in practical situations. Well, you've already done a number of problems in the unit. For example, the problem of the exhibition room organizer, which finally came down to solving a quadratic equation. Well, what we're going to do in this program is to look at some more problems, and then we're going to analyze the problem-solving process itself. You see, we're not just interested in the details of specific problems, but also in the overall strategy to be used when using mathematics to solve practical problems. So, for our first problem, here's Norman Gower.
Our first problem concerns these international standard paper sizes. You may already know that there's a relationship between these sizes. For example, if you take the size A3 and just fold it in half, then what you get is the A4 size, exactly. And if you fold in half again, well, then you get the next size down, you get exactly the A5 size. And so on. You can get any one of these sizes just by taking the next size up, the next size larger, and cutting it in half. So you can imagine a big machine produce a big piece of paper, and by successively cutting in half, you can get all of these paper sizes. So it's economic and it's convenient. But has it got anything to do with mathematics? Well, we'll see in a minute that these standard paper sizes are the answer to a problem that can only really be solved by using mathematical symbols. And the way we approach the problem is typical of mathematical activity and very similar to the sort of work you've been doing in Section 1. The problem that I've got in mind is this, that not only can you get these paper sizes by successively cutting in half, but they're also very convenient to use because they're all the same shape. This property is handy for the enlargement or reduction of printed material. We can print on one size, and if we enlarge by factors of 2, we'll automatically have the correct shaped paper available for the enlarged printing to fit exactly. And the same for reduction of printing. Now that works because all the paper sizes are the same shape. They're specially designed that way because if you take any rectangular piece of paper and just cut it in half, then it's very unlikely that you'd keep the same shape. For example, it doesn't work with this shape. This is twice as high as it is wide. So if we cut it in half, we get 2 squares. Obviously not the same shape as the original. So 2 to 1 doesn't work. Just what ratio of height to width do I need so that when I cut in half, I keep the same shape? Well, this is where I start doing some mathematics. And what I mean by that is that I now start to abstract the problem, represent the things I'm interested in symbolically, and then manipulate the information by manipulating the symbols. Let's call the height x and the width y. Then when we cut the paper in half, we get 2 pieces of height half x each. And they both have width y. Now let's take a copy of 1/2 and rotate it through 90 degrees. We want this piece to be the same shape as the original. We can express this algebraically by expressing the ratio of height to width in terms of x and y. This ratio determines the shape, and we require it to be the same as the ratio of height to width of the half rectangle.
That's an excellent example of the transition from the diagrammatic representation of a problem to the symbolic. And why symbols? So that we can express the problem succinctly and manipulate it. So let's get to work. Here's the equation, x over y equals 2 times y over x. Now Norman has already shown us that if we take a ratio of x over y, that's this to this, to be 2 to 1, it doesn't work. So let's see if the symbols reflect that. I'll put x over y equal to 2. Well, plugging it into the equation, the left-hand side, x over y is 2. Does that equal, let's see now, 2 times, well, I'll put that in, y over x. That's the upside down of x over y, what we call the reciprocal. So if I want the reciprocal of x over y, that's the reciprocal of 2, 1/2. And you can see that that isn't right. Well, what is right? Well, it's this ratio of x over y which is really critical. So let's give it a symbol. X over y equal to r. Now I can plug this into the equation and see what happens. R is equal to 2 times, that's the 2, y over x. Well, again, that's the reciprocal of x over y, but x over y is equal to r, so I want the reciprocal of r, 1 over r. There's my equation. Let's get the r over on the left-hand side. R squared equals 2. Therefore, r equals plus or minus root 2. Plus or minus root 2. I'm interested in ratios of lengths, which have to be positive. So minus root 2 isn't acceptable, but the plus root 2 is. R is equal to the square root of 2.
So, let's analyse what John and Norman have just done and see how it fits into the problem-solving framework given in the unit. It's set out here stage by stage. They began with a clear statement of the problem. What we want to find is the ratio of the sides of a piece of A-size paper. Now, what we know is that whenever we cut a piece of paper in two, we get two pieces exactly the same shape as the original. The next step is to introduce symbols, and that's exactly what John did. X for the height, y for the width, and he called the ratio x over y, r. Now, with these symbols, the problem can be restated, and that leads to this simple quadratic equation. Now, solve the equation. There are two solutions. R is equal to plus or minus root 2, and root 2's 1.414 to 3 decimal places. Okay, then came the final important step, where we interpret the solutions to the equation in terms of the original problem. Now, the answer must be a ratio of lengths, and that's always positive. So the negative number is not a sensible solution to the original problem. However, the positive one is sensible. And in fact, if you measure up a piece of A-size paper, you'll find that the sides are in just this ratio. Well, that problem gave us a very simple quadratic equation, r squared is equal to 2. What we're going to do now is have a look at another problem, and that's going to lead us to a slightly more complicated equation.
Well, this time, let's not cut pieces of paper in half. Let's cut squares off of pieces of paper. And what I'll do is to start with the A3 size. Now, the easiest way to cut a square out of there is to take this corner and fold it across to there. You've probably all done this sort of thing. And then you want to cut this piece off, and I can just do that like this. And then, you see, I'm left with a square. But it's not the square I'm interested in for this problem. The problem I want to show you concerns the piece that's left over, this piece. If you compare that with this, you'll see that they're definitely not the same shape. And that's my problem. Can I find a shape to start with here so that when I cut a square off, then the piece I'm left with still stays the same shape as the one I started with? You can see this won't work. This piece of paper needs to be a bit longer, so this one's a bit fatter. But that's the problem, you see. How much longer and how much fatter? Well, to answer that, really we've got to abstract the problem and go to mathematical symbols. Represent the information we're interested in by symbols. We might as well use the same symbols, x and y. When we cut off a square from the top, the piece we are left with at the bottom must have height x minus y. And of course its width is still y. As before, we take the piece at the bottom, rotate through 90 degrees, and equate the shapes algebraically. That's to say we take the ratio of height to width, the ratio which specifies the shape, and then require the two ratios to be equal.
I think that little equation is beautiful because it sums up the totality of Norman's problem. Let's look at it. He wants to solve this equation. And as before, we're interested in the ratio of x over y, so let's call that r, equal to. Well, we have a bit of a mess on this side. I don't really like the y on top, so I'm going to divide both top and bottom by y. Well, the top, y divided by y, is just 1. And on the bottom, I have x divided by y. But that's just r minus y divided by y, which is 1. I want to work on this equation. Bring it over here, and I have r into r minus 1. I recognize a quadratic equation, so I multiply it out. And that's what I have to work with. But I have a formula, minus b plus or minus the square root of b squared minus 4 times a times c gives me a total of 4, all divided by 2a. Two numbers in here, a plus and a minus. Well, the plus is okay. This is a positive quantity bigger than 1. Plus 1, it's positive. But when I subtract this from 1, I'm going to get a negative. And that really isn't acceptable. We're interested in ratios of lengths, which are positive. So I have only one solution out of this equation. It's 1 plus the square root of 5 over 2, 1.6180339. And how did I know that? Well, that's the famous golden section number. It appears all over mathematics. The Greeks built their Parthenon on the basis of it. It lies behind the problems in coloring maps and in population growth problems, all over the place.
Right, so once again you saw firstly a clear statement of the problem. This was then followed by the introduction of symbols, that's x, y, and r, and then the problem could be restated in terms of these symbols. And that led to this quadratic equation. We now solve that equation using the quadratic equation formula and get the two roots here. And finally, the last important stage, to reinterpret the roots of those equation in terms of the original problem. Now, the original problem is a ratio of size, and so therefore the answer must be positive. And so the positive number is acceptable as a solution, but we've got to reject the negative one. Well, that was straightforward enough. But what would happen in some other problem if, at this stage, instead of getting r squared, we had r to the 5th or r to the 6th? Well, how then would you find a solution to your equation? In fact, in cases like that, there are no formulas that you can use. But you've already seen one method of finding solutions to any equation, and that's the bisection method. We're going to give you another method for finding numerical solutions to equations. It's called the method of formula iteration. Well, we don't actually need this new method to solve a quadratic equation, but just to show you how the method works, we'll solve this equation using formula iteration.
The first step in the iteration process is to arrange the equation appropriately. And what's the equation? Here it is here. What kind of an arrangement do I want? Well, I want something of the form r equals something or other. And of course I have one sitting right here. There are many you can obtain. You could do it by isolating this r. But there's a theory behind this, and I know that the one that's most useful for us involves isolating this r squared. So I'm going to do that here. R squared is equal to, bring the 1 over, then the r. Now I want to divide through by r to obtain r equals 1 over r plus 1.
To start the iterative procedure, what I do is to look at the right-hand side of this rearranged equation. That's 1 over r plus 1. Now, if I replace r by some number and put it in here, then I'll get another number out. Supposing, for example, I replaced r by 2, then we can calculate what we get on the right-hand side. We'll get 1 divided by 2, add 1, and so that equals 1.5. Now that tells us straight away that 2 is not a solution of the equation, because with r replaced by 2, I get 1 over 2 plus 1 is 1.5. These two numbers are not equal, so 2 is not a solution. But the fascinating thing about the iterative method is that I don't just now substitute any old number for r as a second attempt. What I do is to use this value I've just calculated. So 1.5 is going to be my second attempt at a solution. So let's calculate the right-hand side now with r replaced by 1.5. I've got to get 1 divided by 1.5, add 1, and that equals 1.66. Let's just stop at 3 decimal places, 1.667. Well, you can guess what I'm going to do next. I'm going to start for my third attempt with r equal to this, because you see, I haven't yet finished. If I replace r by 1.5, the right-hand side works out at that. These two are not equal, so I haven't got a solution to the equation. And I now use this value, 1.667, for my third attempt. And just to keep track on the calculation, let's introduce some symbols. I'll call R1, R2, R3 my first 3 attempts. Well, the idea now of the iterative method is that you carry on doing this same calculation, and each time you get another number out on the right-hand side, if it's not equal to the number that you put in, then you recalculate. And so you keep on. I'll now calculate an R4 if this now doesn't turn out to be the same, and so on. If you do it n times, then you'll get to Rn, and the next one would be Rn plus 1. And each time you test to see whether 2 consecutive calculations are the same. If they are, then you've got a solution to the equation. Now this sort of repetitive calculation is just the thing that computers thrive on. So what we've done is to program the computer to calculate these successive iterations and to stop when 2 consecutive calculations are the same to 3 places of decimals. .618 was the 8th value that the computer calculated for us. So this 8th value here is the solution to our rearranged equation. If you substitute 1.618 into here, then you get the same number out again. So that's the solution to that. This is a rearrangement of that. So 1.618 is the solution that we're looking for, at least to 3 decimal places. Well, now let's concentrate more on the actual process of what's going on. This time, thinking in terms of these symbols. But we'll keep the numbers alongside them, just so that we can keep track of what's happening. First, we take a number, our value for R1. Then we take the expression on the right of our equation, and we evaluate it by replacing R by R1. We take the output and repeat the process. That's to say, feed it into our expression again. And so on. Each time we check whether the input and output are the same. And we continue the process until we finally get an output which equals the input.
So that's a different way of solving this equation. And it's based on a rearrangement of the equation, this rearrangement. There are, in fact, other rearrangements we could have used, and you'll learn much more about that later in the course. But let's now take a closer look at the iteration process we've just done. Here's a flow diagram describing what's been going on. We start the iteration off by putting n equal to 1. So this is R1, your initial guess. And then you do this calculation, and you generate R2. Then you ask yourself the question, is R2 equal to R1 within the accuracy you're working to? And if the answer is no, then you take R2 and you send it round the iteration cycle up here, and you repeat this calculation, except this time, of course, with n equal to 2. And out pops R3. And so you go on, and you continue the iteration until you find a value of Rn plus 1, which is equal to the previous value, to within the accuracy that you're working to. And that's your answer. And you'll probably remember that the computer stopped when it found that R9 was equal to R8 to 3 decimal places. Right, now you've seen the iteration process, and there's a problem for you to do. It's concerned with the highway code. Now, when you look on the back, you'll find some illustrations of the overall stopping distances of a car at various speeds. And here's the problem that I want you to do. Suppose you want to stop your car within a distance of 100 feet. What then is the speed that you should drive at, bearing in mind that the overall stopping distance consists of 2 parts, the thinking distance and the braking distance? Right, well, we want to find the velocity, so let's introduce the symbol v to represent the speed in miles per hour. That's the unknown that we're looking for. Well, what do we know about the thinking and braking distances? In fact, the figures on the highway code are calculated by these formulas. The thinking distance is 1.0 v feet, and the braking distance is 0.05 v squared feet. So that means that our stopping distance of 100 feet is made up of 2 bits, 1.0 v and 0.05 v squared. So the equation we want to solve is 1.0 v plus 0.05 v squared is equal to 100. Well, after the program, we'd like you to solve this equation using formula iteration. Now, the first step in formula iteration is to choose a rearrangement of your equation. And there are many rearrangements that you could choose. But we've chosen 2 rearrangements, and those lead to these 2 iteration formulas. You'll find them both reproduced in the television section of the unit. And we'd like you to try them both and see what sort of solutions you come up with.